Good morning, all of you TyBsc Physics student. So today we want to start the next chapter of the solid state subject physics, which is X-ray diffraction and other characterization technique. In this chapter, the content described here, the two main part. First part with X-ray diffraction, which consider the Brach's diffraction condition, crystal as a grating, Brach's law and Brach's diffraction condition, Brach's role in reciprocal lattice, evolved construction, experimental method of X-ray diffraction, and analysis of cubic crystal by powder method. This all part which is considered in the X-ray diffraction, and second content which is considered as the characterization technique. And in this characterization technique, the point considered as including the thermal gravimetric analysis, ultraviolet visible absorption spectroscopy, ultraviolet photoelectron spectroscopy, that is principle of this, and instrumentation. And next part which is considered as the scanning electron microscope and scanning tunneling electron microscope. So all this part will be seen in this chapter. So starting from the first point, which is considered as the X-ray diffraction, and we want to first consider what is meant by X-ray diffraction and how it is produced. Starting from the how X-ray produced, the small introduction idea here. So that scientist name which is considered as the Sir Williamson Lawrence Brach. So that the duration of the period which is considered here to 31 March 1890 to 1 July 1971, and was an the Australian born British physicist and X-ray crystallographer, which is discovered in the 1912, and whatever ray which is unknown for the world, so that's why we have to call as the X-ray, and of the Brach's law, which is X-ray diffraction, and which is the basic determination of the crystal structure. So that X-ray which is used to the analysis or the determination of the various types of the different kinds of structure, how it is property, how it is the nature, that all property with the help of X-ray we have to help to analysis the structure of the material. And he was joined the winner, that is with his the William Henry Bragg of the Nobel Prize, which is in the physics award in the 1915. So generally we have to say that what is meant by X-ray. So generally called as X-ray, which is considered as are the electromagnetic wave like the ordinary waves, and hence it shows the interference and the diffraction. Here discuss here the small idea about the wavelength of the X-ray, and that the range of the wavelength of X-ray which is the order of 1 angstrom unit, that is considered as the 0.1 nanometer, and it is the ordinary device that rule the diffraction grating, which it does not produce the noticeable effect of the X-ray. And German scientist Loewe that suggests that the crystal of the 3D arrangement, and that Loewe associate the successfully show that the X-ray diffraction by passing through a thin crystal of the zinc blende, and that crystal ZNS zinc blende crystal structure, which is already seen in the last lecture in the zinc blende structure, how it is arrangement of the Z and S. So this X-ray which is passing through this zinc blende material, so that the observe the diffraction pattern, which is consisted of the central spot and the series of the spot which is arranged, and this pattern which is known as the Loewe pattern. So we have to see in this chapter main point, which is the Brach's diffraction, or what is meant by the Brach's diffraction and what is meant by the Brach's angle. So first of all, consider the point which is Brach diffraction and what is meant by here. So first of all, if we consider the beam of the monochromatic X-ray which is falls on a crystal, and you know that any type of beam which is incident on a material, main three phenomena which is observed there. First one is the reflection, second one is the refraction and transmission, and some types of the ray which is the some of the which is going to deep inside the material. So what happens there? So that scattered by individual atom which is arranged in the set of the parallel planes, and each atom become the source of the scattered radiation. So generally this monochromatic X-ray which is incident on the material, so how it is set up? So that the X-ray gun which is the one side of this, and opposite side for parallel for this, whatever crystal material, that beam which is incident on this, the set which is the parallel set, and this combined scattering of the X-rays from this plane which can be look upon the reflection from this plane, because of this the Brach scattering, and which is usually referred as the Brach's reflection, and this plane are known as the Brach's plane. And for this, the incident angle of the reflection from this set plane which is parallel planes in the phase with the each other, and this considering the incoming rays which is shown in the figure, so that consider as this figure, so that two planes of the wave which is coming from the OE path and O prime A path, and this is incident at the angle of the theta of the plane of the HKL we are considering here, and this rays AP and E prime P which is shown in here. So this AP and A prime P which is scattered at the angle theta from this plane which is shown in this figure. So consider here, if we see the detail of this diagram, so three HKL planes which is there, and distance between the two HKL plane which is denoted by small d, which is considered as the interplanar distance. And for this incident plane light wave or incident ray which is incident on the plane and which is reflected or diffracted or scattered, so that the total path length which is considered as O prime, A and P. So you see that first wave which is incident at the point A, which is making the incident angle theta, and reflected go to the path point for the P, so that path length which is considered as O prime AP, and second path length which is considered as O, which is incident on the HKL crystal plane from the point E and get reflected at the P prime. So this same, and therefore these rays are said to be scattered in phase with each other, and that reflected X-rays which is add up to give the resulting reflection which is strong, and the value of the theta, the X-ray reflection from the different plane, are the antiphase which other, so that antiphase which is considered as out of phase, and that what is meant by the X-ray which is in phase, scattered which is in phase, and out phase which is shown for the next figure. So consider for first figure A, which is the waves in the in phase. We have to see that wave first, wave second, wave third, which is origin at the upside of this crystal plane, and which is go in the sinusoidal rays passing through. And if we see that the summation of wave, that is the total magnitude, we have to see here the increasing the magnitude, so that is called as which is passing through a same in phase. And if we see in the antiphase, so that the wave nature which is from the odd nature, and which is the amplitude which is goes to minimum, and which is shown in the summation of wave n. so as compared to first incident wave, that final amplitude which is the minimum. So this is the idea about the Brach's diffraction. Now next point, see here. So crystal as a grating, or why we have to say that here. So crystal as a grating. So that the nature of the X-ray, it is the essential that they should exhibit the phenomena of interference and diffraction, or you know that the phenomena of what is meant by the interference and what is meant by the diffraction, that is the white light and dark light. So that is overlapping of the two waves, that is increasing the amplitude of the wave, or anti overlapping of the wave and decreasing the amplitude of the wave, that is known by the white, what is meant by white light and what is meant by the dark light, and which is in the study of the interference and diffraction pattern. And this condition, which is well known for the light wave from the theory of the grating, and that is known that the spacing of the lines rules on the grating, which is should be order of the wavelength of the light. And this diffraction pattern, which is the wavelength which is considered about the 6000 angstrom unit, or which is passed through the transmission of the grating of the having 6000 lines per centimeter. So that diffraction pattern which is the observed, and this as the X-ray which is are considered as the shorter wavelength of the lambda, which is considered as the 1 angstrom unit of the diffracting grating should have the 40 million lines per centimeter. So this type of the crystal, and that using the type of the grating one can observe the diffraction pattern. So that in this crystal as a grating, that the scientist Lattice suggested that the crystal which consists of the three-dimensional array, which is regular space atom, and can be served as the purpose of the grating, and the interatomic separation in the crystal, which are the order of the few angstrom unit, that is small, and hence the X-ray which is qualified to be the best undergo diffraction, because the wavelength of the X-ray which is also of the order of the few angstrom unit, and hence this crystal which is acts as the spacing of the grating, which is rather than the plain grating. We want to see here next point, that is the Brach's law and the Brach's diffraction condition. And in this Brach's law or diffraction condition, which is considered the beam of the X-ray wavelength lambda, which is incident at the glancing angle at the theta one set of the parallel planes, which is crystallized shown. So before starting this point, we have interesting here see the point for how the X-ray which is produced. So similarly, first of all consider as the filament which is used, and that filament which is supplied to the current, for example in the small scale about 1 milliampere to 2 milliampere, and parallel to this plane the substance like copper or other substance which is as the used as the acceptor of the this monochromatic beam, which is incident from the filament and which is strike on this material. This material having the very high potential, suppose as the 30,000 volt to the 35,000 volt, that huge amount of the voltage for the accepting of the this monochromatic or the this beam radiation. If we this the filament which is glow, and this radiation which is out of this and which is incident on this the material of the copper, which have the high potential, and this high potential which is supplied here, so that accelerating this charges for the emitting from the filament, and this emitting filament rays which is incident on this material, so that is going to the core shell of this material or outside. So what happens there, if this rays or incident light which is incident on this material. So that what happens there, that energy which is considered as E is equal to h nu, and due to the effect of this high amount of energy, the inner core shell of the electrons which is knocked out, and there is a vacancy which is produced. And you have to know that the property of the any atom or any material we have to get to stabilize its own, and that's why the upper shell or next shell electron which is drop into the or transition into the lower shell, and if this electron which is from the up or higher shell to the lower shell transition, there have the radiate the energy, and this radiate the energy in terms of the h nu, this is known as the X-ray. And for this, in the Brach's law and the Brach's diffraction condition, the consider the beam of the X-ray which is having the wavelength which is lambda and which is incident on the glancing angle on theta on the set of the parallel planes, and this atomic plane which are considered the semi-transparent because of they allow the part of the Brach's they allow the part of the X-ray to pass through the reflect on the other part, and the angle of incident which is considered as the theta, and that first ray which is reflected from the part plane of the plane first, and whereas the second ray which is reflected at the point B lying in the plane of the 2 which is immediately below the atom A. And if we see in the figure, that is the reflection of X-ray from the lattice plane on the crystal. So see the plane first, plane second and plane third. So plane first which is incident on the point A, making an angle incident angle theta, and which is reflected to the path first on the plane first. Now immediately second plane which is incident on the point B and which is reflected for the second, and we have to see here the one trajectory, geometrical trajectory drawn here to point A to point B, and this is incident on the M and N. So this is known as the path difference point or the path difference between the two reflected beam. So this the X-ray reflected from the atom A and the B, which is will be the phase or anti-phase, which is depending upon their the path difference. And if we finding the this path difference of these two rays, so this draw the perpendicular from the AM and AN. So this AM and AN which is draw the perpendicular for these planes which is X-ray which is incident on this atom B, and if we draw this perpendicular, so we want to calculate the path difference between the two reflected beam is, and that path difference which is denoted by the delta which is equal to MB plus BN, and this path difference which is considered as Bn is equal to Mb is equal to d sin theta, with the because that angle which is created at the A point theta, and by the property of the sine which is opposite side divided by hypotenuse, and here d is the interplanar distance, and that's why that path difference which is considered as the d sin theta, and this addition of this d sin theta plus d sin theta, so total path difference which is considered as 2d sin theta. So that the condition of this d which is the distance between two consecutive planes, and theta is the angle between the incident ray and the planes which is reflecting or the glancing angle, and these two reflected beam which is the will be in phase or each other, and if the path difference which is the integral multiple of lambda and antiphase, so if the path difference which is in the in phase, so that is integral multiple of lambda, and with is the path difference which is in the antiphase, so it is integral multiple of odd, that is the multiple of lambda by 2, and therefore this condition which is 2d sin theta is equal to n lambda, here n which is considered as 1 2 3 and so on. So this is If n is equal to 1, that is considered as the first order. If n is equal to 2, it is considered as second order. And if n is equal to 3, which is considered as so this 2d sin theta is equal to n lambda, and this is considered as n is equal to 1 to 3, and for n is equal to 1, that is first order, n is equal to second order, and so on. So this n lambda is equal to 2d sin theta, this condition which is known as the Brach's condition for the reflection, and this relation is known as the Brach's law. Now as the sin theta has the maximum value, which is when, so value 1 for the typical value of the interplanar spacing of, that is d, which is considered as the 1.5 angstrom unit. And if we calculate that n is equal to 1, sin theta is equal to 1, and d is equal to 1.5 angstrom unit, and if we place that value in above formula, that n lambda is equal to 2d sin theta, so that lambda which is given as a 3 angstrom unit, and from the equation this n lambda is equal to 2d sin theta, that sin theta is as it is, and this 2d which is going to denominator for the RHS side, and that equation will become sin theta is equal to n lambda divided by 2d. And if we putting the value of d is there and n is there, so that sin theta which is will become lambda by 3, and when this lambda which is greater than 3 angstrom unit, the value of sin theta which is become greater than 1, and which is not allowed. So know that this is very main important point, that lambda which is greater than 3 angstrom unit, it is not allowed, and hence will be no reflection if lambda is greater than the 3 angstrom unit. So that is main condition. If lambda which is greater than 3 angstrom unit, no reflection pattern which is observed there, and the reflection can be obtained for the smaller value of lambda, and this set of plane that have spacing which is less than the 1.5 angstrom unit, and increasing the number of higher order reflection if the wavelength which is very small. So that increasing the number of higher order reflection, that means that n is equal to 2, n is equal to 3, 4, and so on, so that of the order of 0.0 angstrom unit of X-rays, and this rays which is produce the effect of the knocking of the electron of the atom of the crystal, which is getting the absorbed in the process. And this Brach's law may be used for find the wavelength of lambda of the X-rays of interplanar spacing d, which is known. So summary of this point, which is considered as main condition of the Brach's law, which is considered as n lambda which is equal to 2d sin theta. Here lambda is the wavelength, d is the interplanar distance, and sin theta which is the what is the angle of glancing is there, and what is the value of theta is there. So now next point which is interesting to see here, so Brach's law in the reciprocal lattice, and this Brach's law in the reciprocal lattice which is considered the diffraction of the X-ray which is occurs in the various set of parallel planes which is having the different orientation and different interplanar distance in some crystal, and there are the number of set of parallel planes with different orientation. So this problem was simplified by the PP evolved by the proposing a new type of the lattice known as the reciprocal lattice, and already last chapter we have seen their point what is meant by the reciprocal lattice, and this crystal lattice be conveniently represented by the reciprocal lattice. Also the photograph of the X-ray diffraction, which is find to easier the description in terms of the reciprocal lattice rather than the direct lattice, and already see that reciprocal lattice vector that capital A bar, capital B bar, capital C bar, and direct lattice vector it is small a bar, small b bar, small c bar, and what is the relation between this, and what is the property of reciprocal lattice, which is seen already in the last chapter. So that for this construction of this reciprocal lattice to a direct lattice, that the origin at some arbitrary point which is drawn normal to the every set of the parallel planes, which is see in the figure of the 2.4. So that Brach's law and that dotted line which is draw a normal to the plane and of the direct lattice, and the length of each normal which is should be equal to the reciprocal of interplanar distance. So this length which is equal to the interplanar distance between these two planes, and that for the corresponding set of the parallel planes, and the terminal point of all normal from the reciprocal lattice. So in the see in the figure, so that well collimated beam of the X-ray of frequency nu which is incident on the crystal, which is shown in the figure, and you have to know that monochromatic X-ray or whatever beam which is incident in terms of the electromagnetic wave having the energy is equal to h nu or h cross omega, and this frequency of the X-ray which is h nu prime and or h cross omega, and that omega prime which is nothing but the twice pi nu prime. If we see in the figure that incident X-ray which is making the angle theta which is incident angle, and reflected so which is incident in which is considered as the wave vector k bar, and reflected X-ray which is the considered as the wave vector k bar prime, and the plane which is have the separation distance d which is the interplanar distance. So this plane which is considered as a set of plane. So for incident energy X-ray which is equal to reflected energy of X-ray for k vector wave number k bar and k bar prime. So incident energy which is considered as h cross omega, and reflected energy which is considered as h cross omega prime, and this h cross which is get cancelled, so that consider that energy which is nothing but omega is equal to omega prime, and that vector k bar and k bar into the wave vector which is the direction of the propagation of incident and reflected X-ray. And if we see the condition, that is the space between the parallel planes which is free space, so that magnitude which is given by calculated mod of k bar is equal to omega by c, and mod of k bar prime which is omega prime c. So that here the new factor coming from c which is considered as the velocity of electromagnetic waves or X-ray in the free space, and that using this condition for equation first and second, so that coming the condition mod of k bar is equal to mod of k bar prime, and this is assumed that k bar and k bar prime are related to the equation which is coming from k bar prime is equal to k plus g, and g is the reciprocal lattice vector which is joining the tip of the k bar and k bar prime. So for this condition, so that k bar which is equal to k bar prime is equal to k bar plus g bar, and this condition which is here for the k bar prime dot k bar prime, that is considered as the product of two vector of k bar plus g, that is the product of two times. So doing this multiplication, the condition which is coming from arise from k bar prime square is equal to k square plus g square plus 2k into g, and that is prove this condition for k bar is equal to k bar prime, and this is twice k dot g plus g square is equal to 0. So this condition which is known as the Brach's diffraction condition which is in the reciprocal lattice. So this is the very important chapter, and summarize of this for starting this, what is mean by the diffraction condition, how X-ray produce, what is the main condition diffraction condition, or what is the in phase out phase, or what is the condition of the Brach's law which is considered as the n lambda is equal to d sin theta. Lambda is the wavelength, is the interplanar distance, how it is calculate the wavelength as well as the interplanar distance between them. So, and what is meant by the Brach's law in the reciprocal lattice. Now, next lecture we have to see here what is meant by the evolved construction or experimental method of the X-ray diffraction, which is will be seen in the next lecture. So, thanking of you.